Hello everyone and welcome to ME304 Machine Design. We'll be using the Shigley book for this problem. So if you need any tables or charts, go to the Shigley book, Machine Analysis and Design. So the problem we have right here is an M14 by 2 square thread power screw formed from so on and so forth. Go ahead and pause this to really get acquainted with the problem. I'm going to go ahead and go straight into it. So moving on here. Looking at this problem, what you first have to do is figure out what the rising torque is. That's what you have to start with. You have to figure out what the stress is on the bolt as you're going through the problem. So, finding rising torque. This is going to be not a terribly long problem, but certainly not a short problem. So, any part that you already know or are familiar with, just go ahead and skip ahead a minute or two. So, rising torque. The equation you use for rising torque is TR is equal to FDM, which is the median diameter, all over 2 times L plus pi FDM, all over pi dm, minus FL, the length of the bolt, the coefficient of friction for the rising torque, plus FC, this is the coefficient of friction for the collar of the bolt, DC, diameter of the collar, all over 2. So this is the total amount of force that's being applied, friction force, then the mean diameter, coefficient of friction of the threads with the bolt or the screw, basically. So defining dm, it's equal to the actual diameter of the bolt minus the pitch over 2, which is equal to 14, because in the problem, M14 by 2, it is 14 millimeters. 14 millimeter diameter. The pitch is equal to 2. Well, wait, sorry. Yeah, pitch is equal to 2. Just want to make sure I didn't say that wrong for reading bolt. So we've got 14, pitch is 2, again for the bolt definition. So the bolt definition gives M14, which is the diameter and the pitch. Alright, which is equal to 13 millimeters. And L is equal to P, which is equal to Z millimeters, or 2 millimeters. Sorry, I apologize. I misdefined this L. It's not the length of the bolt. It's the pitch length, which is slightly different. It's basically how many threads you have for a certain distance. So we have length of one thread per millimeter, basically, is what this is. So it's basically, if you have a bolt like this, L is from here to there. But that also happens to be the pitch. When they ever vary is when the pitch is always from tip to tip, basically. But L can vary if you have a double threaded system. So like you have a thread here and a thread here, but they're not the exact same thread like a normal spiral. It's 2 coming down. So that's when the L would be different from pitch. But normally your professors don't really bring that up. So in this case, L is equal to pitch. So moving on, doing this calculation, TR is equal to 10 times 10 to the 5th newtons, which is the force. If you go back and look at the problem, 13 times 10 to the negative 3rd meters, which is dm, all over 2. And I'm going to go ahead and multiply that down here because I made a mistake. Putting this stuff over here, I should have moved down further. So multiplied by 2 millimeters plus pi times 0.08 times 13 millimeters all over pi times 13 millimeters minus 0.08, both given, the friction coefficients given, times 2 millimeters. And as you can see, I didn't convert these millimeters to like 10 to the negative 3rd because they cancel out, top and bottom of the equation, plus 10 times 10 to the 3rd newtons all over 0.06 times 20 times 10 to the negative 3rd. Actually, can't read the notes that I was given here for this one. I think it's meters. Yes, meters. Should be, yeah, meters. Because it's the diameter of the collar. It had some weird H on it there, so I was a little bit confused for a second. But okay, go ahead and do that. So those are all values. They were given values or values that were calculated from these two. So it's pretty easy to get the rising torque because we were given the force that's being applied down onto the power screw. So then TR is equal to 14.4 Newton meters. So that's the torque. Rising torque is the torque required for the screw to lift something up off the ground. Okay, now calculate the lowering torque. Torque TL, which is all very similar. The only difference is this section right here. This plus goes to the denominator, this minus goes to the numerator. So kind of a subtle difference, but the difference still the same. So 10 kilonewtons already times 13 millimeters all over 2 times pi times 0.08 times 13. Oh, sorry. Probably can't see any of that. Okay, there you go. Millimeters minus 2 millimeters, which is the minus, the switch there for lowering. Pi times 13 millimeters plus 0.08 times 2 millimeters. Okay, plus 10 kilonewtons times 0.06 times 20 millimeters all over 2. If you calculate that out, you'll get a TL is equal to 8.0 Newton meters. And that makes sense because when you're lowering something down, it's actually almost helping you when you're using a screw because it's pushing down. It doesn't take as much effort to unscrew something downward when there's a force put on it. So that makes sense. If your TL is not lower than your TR, your rising torque, then you made a mistake somewhere. That's basically how that goes. Okay. So now, excuse me, we have to use this other equation to continue on with life, which is sigma prime, which is equal to 1/2. This is the three-dimensional von Mises equation, basically. Sigma x minus sigma y. My professor gave me the notes for this problem, and I can't hardly read some of his handwriting on some of these deals. So I apologize. Sigma y minus sigma z squared plus sigma z minus sigma x squared plus, this is a long deal, tau xy squared plus tau xz squared plus tau yz squared. And all that to the power of 1/2. So the three-dimensional von Mises that you have to use for screws is really long and nasty, basically. But because you have to find the stress in every single plane. So the zx plane, yz plane, and xy plane. So, going ahead and doing that, finding Ft. Ft is equal to 0.38 times F. I got, again, read my professor's notes. Man, it's confusing. Okay. This is part of the equation. Part of the equations used within screws. You should have been introduced to this a little bit, so I'm not going to go into it very much. But what you do is you use this Ft, sigma x, in order to calculate sigma x, which is equal to 6 times 0.38 F all over pi dr p, where dr is equal to d minus pitch, which is equal to 12 millimeters. So 14 minus 2 is equal to 12 millimeters. Let me see if I can find this equation for you, this stress equation for screws. Hopefully you've been shown to it, so that's not surprising, but I just want to make sure that nothing jumps out at you weird. It doesn't look like I can grab it from my notes fast. So this equation, just using dr here, is about the only trick to it. And the 0.38 F is kind of based on the circumstances. because it's where this is normally multiplied by NT if your professor hasn't introduced you to it, because NT is usually out here. But for this situation, NT is equal to 1. So hopefully that makes that a little bit clearer for you. It's a screw equation that's just set towards these specific screws. I don't really have much more to explain with it right now without having to go into a whole nother lecture. So I'll try to do another problem with this some other time. So, okay, so sigma x, if you calculate that all out, moving through life here, sigma x is equal to 6 times 0.38 times the force, which is 10 times 10 to the third. The force acting downward on the screw. All over pi times 12 times 10 to the negative third meters. Sorry, it's meters, that's not an n, that's an m. Times 2 times 10 to the negative third meters. Again. And you multiply that all out and you get 302.4 megapascals. Okay. Sigma y is going to equal to 0 because on screws, sigma y always equals 0. Sigma z is equal to negative 4f all over pi dr squared, which goes to negative 4 times 10 times 10 to the third newtons, all over pi times 12 times 10 to the negative third meters squared, dr, again, radial diameter, which is equal to negative 88.4 megapascals. Sorry. Okay, so we got those values now for our von Mises stress that we can use later on. These are all the principal stresses. Okay, so now tau xy is equal to tau xz, and they are both equal to 0. Because, let me draw this out here. If you've got a screw and you've got a thread sticking out the side, and it's got a collar sitting on it here somehow, something like that, whatever. It's got a force acting down on it right here, so it only has shear in the one plane right here. So that's why tau xy and tau xz are equal to 0. So tau yz is equal to 16 Tr, rising torque, all over pi dr cubed, which is equal to 16 times 14.4 Newton meters, where we calculated this earlier, times pi of 12 times 10 to the third meters cubed, which is then equal to 42.4 megapascals. Okay, so still cranking along here, we're getting a little bit closer. So now if you put those back into the von Mises stress equation, I'm not going to put those values in because you know what the equation was. Showed it to you just a second ago. There we go. Von Mises stress right here. Sub all these values that we just got back into here and solve it out. I don't want to spend time writing that out. So sigma prime is going to be equal to 362 megapascals. Oh, sorry. Not cross out and underline. 362 megapascals. Okay, so now the problem asked us to use DE theory to finish the solution and find the margin of safety. So using DE theory, the way you define margin of safety is you have the margin of safety is equal to SY in tension, the yield strength in tension, which you can get from the charts in the back of the book. Sigma prime times the factor of safety minus 1. And if you're not comfortable with factor of safety by now, this is basically just an increasing factor of what the stress is going to be imagined to be to make sure your system is strong enough. So, using table A20 in the Shigley book that we use in the Shigley machine design and analysis book in this problem, dash 20 SYT is going to equal 580 megapascals. On the back of the book, for the type of steel that we're using, so MS is going to equal 580 all over 362 times 1.5 which is our factor of safety, minus 1, which is equal to 0.068, is our margin of safety, which is just barely, but it's okay. So our system meets the requirements that we wanted to, but this margin of safety is actually pretty small. You want it higher if you're actually designing something. Alrighty then, so that's how you use analyze a power screw.